Hello, dear students. Welcome to our experiment in measuring surface tension, wetted length, and contact angle. The purpose of this experiment is to find the contact angle, and we are using the so-called force tensiometer. And this is a type of this device because it has the upper parts like a sensitive balance, where it measures the forces that we have at the metallic part or the solid part hanging up here together with its interaction with the liquid phase that will be put in such a vessel in this platform. This is one way of doing things, of measuring contact angle. The other way is similar to what we have here. We use a droplet shape, which is the liquid part similar to what we have in the vessel, against some solid surface, which is like the part that will be hanging here in the balance. And this angle is suspended inside the liquid droplet between these two vectors. They originate at this common point between the liquid solid surface and another liquid, or maybe gas, which is air in our case. So these two rays originate from this common point where the air, in our case water and solid, meet. One ray is between liquid and solid, the other ray is between liquid and air. So this suspended angle here is the contact angle. This is the other approach, to measure it using geometrical shape of the droplet. However, our case will depend on measuring forces. That's why we need to find the so-called surface tension and then the wetted length. And wetted length is very special to this method. Otherwise, we will not use it in this graphically oriented way. So what's surface tension? It is basically due to this. We have these circles like molecules of compounds. For water, it will be water molecules. It is a surface property, that is why it's called surface tension. It happens at the surface. What is the surface? The free surface between water droplet and air, and the surface between water droplet and this metallic surface of car body. So what happens is like this. These metal molecules are very happy, they are at rest almost, because they have equal forces all around, in all directions. However, those at the boundaries, or at the discontinuity, at the ends, at the edges of the droplet, like those with the air, they are pulled down or inside the liquid, and not as much by the air. That's why we have such a stretched sheet, as if we have such a sheet that is very stretched. And you can see it like this. So here we have a mosquito that is walking on the water surface due to the fact that the surface is like a stretched sheet. Here, the glass is not spilling out the water immediately because this sort of stretched film that will hold it in place. Another way to see the surface tension is using the capillary tubes like these three. This is the smallest in diameter, inner diameter I'm talking about, intermediate one, and this is the one with the largest inner diameter. So the diameter increases from going from left to right. What will happen is this. And you see, we have the highest rise here in the narrowest inner diameter, intermediate and smallest height in the widest inner diameter. So this is one way to see the surface tension in action. Another example for surface tension, here we have this astronaut in the International Space Station. She's brushing her teeth, and this is a bucket of water, and you can see water droplets. They are flying all around in spherical shapes, not in any other shape, but in spherical shapes like this. Definitely she's surrounded by air, so this is the action of surface tension of water when surrounded totally by air. Another example is placing this metallic sheet that is cut into this way, maybe to reduce its mass a little bit. It is gently placed the surface of water and it's floating. We may think it is floating due to that it has got a smaller density, which is not true actually. Why is this? Because this gentleman injects some fluid, probably soap, which is like a surfactant, to reduce the surface tension. We'll see what will happen to this metallic object. It sinks. So it is not a matter of density, it's a matter of surface tension that has been reduced too much to the extent that it cannot hold the plate anymore. One last video that shows what is surface tension, which is force per unit length. It is like this. We have this structure with this movable rod immersed in soapy water. Then what will happen when we break this small rectangle? We have the rod moving to the other side. So the other side, the unbroken one, has pulled the rod towards its end. This is the surface tension in action, which is force acting on the rod per unit wetted length of the rod. And this brings us to our experiment. As an important initial step to get started, we have to clean the vessel where we will put our liquid part of the sample. Namely, we will put once water and the other time in butane. And we will also, after this, clean the plate or the strip of solid that will be using in measurement. Cleaning is very important, otherwise any contamination or any foreign particles or any sort of grease or fat or whatever dust can be available will corrupt the measurement. So let me first clean it with this soapy water, then I rinse it with distilled water, followed by alcohol, and then finally distilled water again, and then I use a tissue to dry it up before I put in the sample. So let's get to work. Now, I've cleaned these two vessels and the cylinder, graduated cylinder, and I filled this vessel with about 50 cc of tap water from this beaker using this graduated cylinder. And it is good to keep the volume not too much and not too little, and to make it consistent through the experiment to eliminate the effect of volume of liquid sample from the measurements. Now, this plate will be used in the very first part, which is the surface tension. We will be using it with water to determine its surface tension. The plate has been cleaned with soap, rinsed with distilled water, and then ethanol, alcohol, and then rinsed again. And finally, it will be put into this flame. This last part is not to make it cleaner, it is already clean. Like the flame is important to make it very active. So I keep rotating it like this in the flame until it's almost red hot, which is this state. Okay? Now we are ready to get started with the very first part of the experiment. So I put the vessel here. I hook the plate up there. I move the vessel up. Now I need to make them close to one another, but the plate should be kept dry and clean in the air and not to touch the water surface. If the camera can zoom in, I can see some reflection of the plate on top of the water. So this makes me sure that I'm close enough, but not too close. Okay? So I'm ready to start the module here. So this is a software. It's got two parts. This red part for surface and interfacial tension, and this green one for the contact angle. We use this later. So let's start with this one. I can use close first this database. So I create a new database in this pass and name it as bench 3022 string 20. Now can create new measurement. Actually make a folder for today, which is Monday. March 2020. And in this folder, I can go to new measurement, surface tension, SFT, and interfacial tension, IFT. We'll be using surface tension. We have ring, plate, and rod. We'll be using the plate, which is the one I've shown you. This is a tab loader. These are values for the plate, standard values already saved in the software. The liquid name is water. Gas is air. We have here air, nothing more. If we need to inject some other liquid, some other gas, which we don't have its facility or accessory, it could have been done through this big hole in the upper right surface. For the procedure, we will give it 10 values to get an average mean value for 10 measurements. And for the vessel, we'll change it as given in your lab manual to SV20 plus. So this is the one correct one with the correct dimensions for our glass vessels. Okay, we place it in the folder and in the database. Now we can get started. To go to the start measurement. Here, if you notice, it's telling me to put the liquid into the sample vessel with a volume greater than 35 milliliters. We do have 50 milliliters. Clean the plate, which is a standard plate, and fix it at the balance, which is already done. Move the liquid close to the plate, is also done. Downstairs here in the measurement, the software will give us some indication of what it is being done. So now the balance is locked, and once I click OK, the software will start the experiment. It will unlock the balance, tear it, so the weight of this plate is removed from the calculation, because you know it's force tensiometer, so it measures forces, and from there it calculates. And then it will start to approach the surface. Until it reaches the surface, it will detect the surface by a sudden upward force. So by there, it knows where the surface is exactly located with respect to the plate, and then the experiment proceeds. So okay, unlocking the balance, setting it, take balance to 0, surface detection. It will give us a peep. Yeah, this is a peep. And if you see here, this shape like an upward mustache or lamelle, which means that the plate is pulling up the liquid surface. And here we have the data being collected. It will collect up to 10 points actually. So what was done is that it detected the surface, went into the liquid a little bit, and then it went up again to be at the surface free level. So this part of the experiment has been done. It's very quick. We go to the data tab here. These are 10 points, as you see. I select it all, copy, and then take it to this blank sheet and empty file. I paste it. I save the file by today's name, Monday, 30 March 2020, and name this sheet as an SFT for surface tension. Then we are instructed in the experimental part so in this part, we have the shape, we have seen this lamella which is pulling upward by the plate. And we have this equation, as we have seen in the demo, the video, that the surface tension is a force per unit length. To be able to do this, I need to know that this force is in the tangent, this vector F tens, which can assume in general some acute angle between it and the normal direction, F normal. And F normal is a direction where our device, our balance can measure. So the balance is always measuring in the normal direction, downwards normal direction. It cannot measure in any oblique angle like this. So then the geometry or trigonometry actually will help us do this. So I need the component of F tens along the normal direction. So I replace F tens by F normal over cosine contact angle. And this is actually the contact angle we have seen earlier. It is the angle between the tangent to the liquid and the normal with the solid surface inside the liquid. Okay? So this is the equation. Now I need to find this surface tension. F normal is always given to me by the software, as you'll see right now. L is known because the plate has got standard dimensions and they are known already. So I have two unknowns actually in this single equation. Surface tension sigma and theta c, which is the contact angle. To be able to solve this, one of them should go away, and actually the contact angle will go away. Why is this true? This is true because we have used the special plate that is clean and red hot. And this is important to assume that the contact angle is very minute, actually zero. So we have a perfect wetting. That's why we have this pulling up of water by the plate. So the plate has got the water pulled to it, so the plate is perfectly wet by water. Accordingly, this theta c is assumed to be zero, and this is a fair assumption. Actually, in the manual, I'd like to show it to you here. If we write plate, okay. So here we are talking about measurements using the surface tension. In this part, it's talking about contact angle, and it reads angle between the surface of the measuring body, our plate, and the force vector of the surface tension. This angle, in order to be able to measure the surface tension or interfacial tension, this contact angle must be zero, which represents optimum wetting of the measuring body. Therefore, the materials with highly energetic surfaces like platinum or platinum iridium alloy are therefore used. And this is the reason why we have been using this particular plate and making it not just clean but red hot to be very energetic, and consequently the assumption that the contact angle is zero is valid. So this is the result. Here I've added the width and the thickness for the plate to calculate the wetted length, which is a parameter of the plate as written in your lab manual. These are the forces that we'll be using, force normal over the wetted length here. I calculated one of them, and you should do the rest here in these cells for the other values, for the other 9 values, and to get the average. For this one, I've calculated the force, which is in millinewton over weighted length in millimeters, so this is the value. And to compare it against some tabulated standard values for known liquids, these values are given as a surface tension against temperature for some liquids, and the units is given in millinewton per meter. So I've changed this millinewton per millimeter to millinewton per meter as such by multiplying it by 1000, because the millimeter is in the denominator. And we are at the temperature of 21.69, which is almost 22. If you go here, 22 for water in this column, it will be 72 here. This is water. It will be 72.45.